Okay, good morning and welcome. So this week we are going to start talking about a more general form of energy. So maybe I can just remind you where we are in the class. So we started with Newton's laws, and we showed that they are pretty useful to describe the motion we see every day. And there are like forces like gravitation, and then Newton's laws combined with gravitation is actually very, very powerful and predicts the planets very accurately. Last week, we started to talk about a new concept. We introduced work and we introduced energy, and we said that was actually an alternative way of solving problems. Some problems were complicated in terms of Newton's equations, but when you express them in terms of energy and work, they were much simpler. So this week, we'll continue along this line, and we'll actually introduce a more powerful law of nature, conservation of energy. Okay. All right, then I'm going to introduce a terminology or like a classification of forces. And for that, I want to start with actually an example. And this example is, okay, maybe I can first introduce the example and then tell you what it is, which actually is a little bit easier. So, and the example is about work done by gravity. Okay. Maybe I can write it. Work by gravity. And I think we actually like studied this last week a little bit. And the work done by gravity, let's consider this picture. There's like a mass, and you are taking this mass from some height y1 to another height y2, which is about h different. And the key is the path is arbitrary. I can take it like directly, I can take it in like any complicated way I want, and I don't specify the path. And for that, work done by gravity is, I think, as we know from last week, is force as a vector dotted with displacement as a vector. So this force is, okay, this thing is mg, and it is along y direction. And if you zoom into dl, dl is in some direction that's along the path. But the key is if you take the dot product is written always in terms of this theta between the vertical and the path. And when you take the dot product, you project the L to this little segment. Maybe I can zoom in just a little bit. So the L is some path, and with the dot product, you're projecting along this segment, which is exactly the definition of dy. So I'm going to write that. So this is equal to, let me put the minus sign here. And actually mg is constant, so let me put that also here. And this is going to be dy. And the difference is from y1 to y2. Okay. And you can take this integral. This is like an elementary minus mg. And what is it? y2 minus y1, which is equal to h. Okay. So the key about this is like this work done by gravity only depends the difference between initial and the final positions only depends on height. Okay. But it does not depend on the path, not on the path. Okay, that's the key. And we say that when the work done, okay, here's the definition. When the work done by a force does not depend on the details of the path, we call that force conservative. Okay. So the conservative is now a conservative force. So work does not depend on the path. Whereas for non-conservative forces, the work intimately is connected with the path. If you have a longer path, you have a different force. If you have some curly, weird path, you have a different work. So it's like totally path dependent. Okay. And generally, as a rule, okay, maybe I can write it here. So conservative forces, conservative, maybe, okay, I don't know, let's try. Conservative forces depend on things like position, whereas non-conservative forces depend on things like time. If there is like a time dependency, that's non-conservative, or velocity. I think an example for this is like a drag force. When you drop an object, the force on the air, the force on the object by the air is velocity dependent. That's how you get the terminal velocity. Okay, any questions? Why we use integral f doesn't change? Because yeah, that's the most general expression for work. If you want to write it like this, that's also fine by me. I'm used to writing integrals. Here is like a little corollary of this observation. Let's consider these two examples. So the work done, okay, I want to consider an object at position 1, and I want to displace this object to position 2. And I'm assuming there's only conservative forces. It could be gravity, it could be whatever, okay? And the question is, let me just say the work done on the object from this conservative force is like something like from 1 along the path A, let me call this W. Okay, some work, uppercase W. And since it doesn't depend on path, I can safely say, okay, work done on the object along the path B is also W. This one is also W. Now let's consider this case, this second case. The path A is exactly the same. There's no difference about the path, but the path B is reversed, right? This one is a reverse direction in compared to this one. This is up, this is down, if you like. So my question to you is, what's the work done on the object from point 2 to point 1?
W?
Yes, thank you. This is exactly what it is, because here you can think of like integral. If you reverse the limits of integral, we are going to get an overall minus. And here's the overall. Reverse my perception a little bit about this picture, and I can think of like a loop. And this loop, I start at 1, go to some point 2, and come back. Now I want to introduce a new thing. Now we already introduced the conservative force. That's what it is. And I'd like to now introduce potential energy. Once we know the conservative force, it's easy to introduce potential energy. Work done by conservative forces is potential energy. This is work done by conservative forces. So if it is gravity, it's like gravitational potential energy. If you are talking about a spring, there's like a spring potential energy. But if you are talking about a non-conservative force, there's no potential energy related to that. Okay. And here's the example. So here's the example, like why do we call it potential, right? Why is it potential energy? You can think of something like this. You have a block, and you lift this block to a height h, and you ask yourself how much work is done on the object by the gravity, right? Or by your hand. And of course, you are assuming it is like moving with constant velocity. And I think this is like elementary. Maybe I can just write the result. The W external, in this case, is equal to like change in potential energy which is equal to mgh. So maybe you can consider this like you can compare this to the work energy principle, right? It's kind of like work energy, like work energy principle, but here the work is done by your hand, but the energy is the potential energy. Okay? The change in potential energy is equal to work done by your hand. And if you release this at this point, of course, if you take your hand out, this thing is not going to stay there because there's like a potential. That's why we call it potential. It's going to fall back and it's going to gain kinetic energy. So from here, we define some gravitational potential, if you like. U gravitation is going to be equal to mgh. Okay, any questions?
I would like to add something about the first question. Shouldn't the integral go from y2 to y1 because it falls?
So it is like the force, right? It is, so this question?
Yes.
So it is the force, and I'm talking about the gravitational force here, F gravity. And the L is the path from y1 to y2. So the gravity is minus mg minus y hat, and dl is, I think, from the cosine dy, and the limits I start at y1 and end at y2. And it's negative because we are talking about the work done by gravity. There is like a force of gravity on the object, and that's like minus because force and the displacement are in the opposite direction. Of course, there is some hidden other agent we don't talk about. Maybe it's a hand, maybe it is somebody is pulling it. We are only looking at the gravity here. And it is negative because force and displacement are in opposite directions. This is not potential energy. We define potential energy here, which is positive.
Okay, I see. Thank you.
Yeah, this is a little bit of like yeah, I think it's not very nice, but it is what it is. So the key here is, I think what is important is physical, okay, maybe I can write it as a bullet. What is physical is change in potential, right? So the important quantity here is what's the difference between these two things. So that's the, like, there's no absolute potential. What is the potential here? It is, there is like some arbitrariness up to a constant, but the potential energy difference between y1 and y2 is not arbitrary. It is mgh. So that is the physical quantity. Okay. And also another thing is this potential energy here. Maybe I can also write this as a bullet. So potential energy is a property of the whole system. In this case, it is Earth plus the block. Okay. I think we are just introducing some stuff you probably already know from high school, and we wanted to use this last week, but last week we wanted to just slow down and like go step by step. Okay, any questions or objections? All right, so let's continue. Now I want to consider like a general case of potential energy by a general force. Okay, maybe I can write it here. So I want to consider the potential energy done by a general force. Okay. With this, let me just put general force. we should be conservative to define potential energy. And the form is, what is it? What it should be something like, okay, here's my definition. Change in potential energy by a force. Okay, I'm looking at here. So work done by gravity, okay, the work done by gravity was minus, but the gravitational potential energy was plus. So like exactly like you asked, it is it is not nice to carry this minus sign around. So I'm going to put that minus sign here. Work done by force is going to be equal to minus the force times displacement. Okay, and it is from position 1 to position 2. Hopefully that makes sense. So this is also like for conservative forces. Just to remind you, because there's no potential energy for non-conservative forces. Okay, here are the examples. Like for example, for gravity, U, okay, maybe I said delta U, gravity was equal to, okay, minus the force that the L, exactly like you pointed out. The minus here cancels with the minus above, so you are going to have some mgh. And you can do the same thing with spring. Spring delta U spring minus F spring. The L, I think we introduced this last week. You have some spring, is like some mass, and you are, let's say, displacing this by an amount x. And I think we calculated the work done, and there's like an overall minus. Okay, we are calculating the work done on the spring. So work done on the block by the spring as you move, and force and displacement are opposite. This thing is minus, but since we introduce an overall minus, it's going to be plus. Let me write that. It's going to be 1/2 k x squared. I think we like introduced this, calculated this last week briefly. Work done on an object by the spring. Okay, any questions about this? Here
Why
now,
is there a general negative sign before the formula?
Because that's how I decided, right? If I didn't put the like, I mean, the way I do this is like, okay, I do it, and if there's no minus sign, there would be a minus sign, and exactly like you pointed out, that's not nice, right? For example, here. So I am calculating the force, and I am calculating the work done by this force on the object. And if the particle is going in this direction, I have an overall minus sign. But what is happening is, as you go from here to here, your potential energy is increasing, right? The potential energy actually should be positive here. So that's actually a little easier to work with when I introduce it here. So I did exactly the same thing. Like if I put the minus sign, I can think of potential energy, which is a positive quantity. Okay. Of course, you can just think of this like a overall definition. Yes, people are giving thumbs up. I guess I don't know what that means. You can think of this like an overall definition, but it's easy to see why it should be minus, right? Just think of this gravity example. If you didn't have the minus, you would have an overall minus here, and your gravity would be minus mgh. Good. Does that make sense?
Yes, teacher.
Now I want to reverse. Okay, so here the logic was, given the force, calculate the potential energy, right? Given a general force, calculate the potential energy. But what is interesting is there's actually like a reverse logic. So given the potential energy, The question is, can you calculate the force, right? And of course, we can. For example, can use this definition. We can take the derivative of both sides if you like. Okay, we said it is defined up to a constant, so let's make it like indefinite integral. So this is going to be f. Let's think of one-dimensional example to make it simple. F dx. F is one-dimensional, could be positive or negative, and dx, and then it's defined up to a constant. And now I take the derivative of both sides with respect to x. So I have du dx is equal to, okay, what is the derivative of integral?
Functions itself.
Yes, exactly. It is the function, for function itself. That's why people call integral sometimes antiderivative. So this is going to be minus f. Or I can write it like force is equal to minus u dx. But I know this is in x direction because everything is in one dimension. But in the general case, I can make it like a vectorial quantity by using f is equal to minus del u del x along x direction plus del u, okay, minus del u del y direction minus del u del z direction. And here the partial derivative means take the derivative as if everything else is constant. For example, if you are taking the partial derivative with respect to x, you're assuming u is only a function of x and taking the derivative, and the same for y and z. Partial derivative is very convenient, very easy thing to do. Okay. And here, this is the definition of the force. Sometimes people will, maybe you'll see things like this. Force is equal to minus gradient of potential energy. Okay. So this thing is exactly this is. Okay. The definition of this thing is exactly this line. Anybody feeling uneasy with this new concept?
John,
Yes.
I still don't understand the thing about the minus signs with the gravitational potential energy.
So I think the way I use this is like I kind of memorize it. But if I want to like convince myself why there's like a minus sign, I always think of this gravitational example. So from high school, we know the gravitational potential is mgh. This is what we know, right? This is easy to understand. If you just place something, some h, its potential increases. But now I am saying that let me calculate the work done by gravitational force. Let me forget there is anything called potential energy, and let me calculate the work done on the object by the gravity. And it is this line, right? And we know that if the force and displacement are in the opposite direction, the total work is going to be negative. But here I obtained, okay, by calculating this integral, I obtained mgh. Then I'm saying, okay, there's like overall minus sign. That doesn't make sense. Let me define the potential energy with an overall minus sign so that I have what I wanted to have in the beginning. Okay.
I see. So the minus sign actually denotes that's the work done by gravity.
Yes. So
Yes.
minus
And that's different from the gravitational. Well, it's not different in magnitude, but then in direction.
Yes, there is like, so the work done on an object, of course we are talking about force, conservative force, is the minus the potential, or you can reverse the direction. I'm saying the same thing in the opposite way, but I think that's the logic. Okay.
Yes, I understand now. But then if I'm told to calculate the work done by gravity, for example, now, so I will take the direction of motion into consideration. That is, for example, you know, that's in the example, the object was y1 to y2 in the upward direction, and then, you know, the force of gravity is in the opposite direction, so that's why I have minus ultimately. So what if it was the reverse? I would not have my work done by gravity as minus, because then the that's on the direction of motion will be downward, and we have gravity downward as
Yeah,
well.
yeah,
So
yeah, I got you exactly. So suppose, suppose you are going like not so. In my example, I was going from here to here, right? Suppose you are going from here to here. Okay. Suppose y2 is your like exactly like you said. Let's reverse the situation. I'm going from a higher altitude to a lower height, if you like. Okay. And here's again the same logic. Let me just write it exactly here like I did. So first thing I say is like, okay, let's use the high school knowledge. What is the change in potential energy, right? If I go from here to here, what is the change in potential energy? So I have some mgh, and if my reference point is here, I have minus mgh, right? Potential energy decreases because my height is decreasing. Do you agree? So this is the potential energy. And now let me calculate the work done on the block by the gravity as it goes down. It is exactly like here, like exactly like you said, F dot dx. Now force and the gravity are in the same direction. The whole thing is mgh. Now I have an mgh in the work, but I needed a minus sign because potential energy is decreasing. So either way, you have to put a minus sign.
I understand. So sorry, I also wanted to ask. So is potential energy a scalar or a vector?
Yeah, good question. It is, yeah, energy is scalar, right? Potential, like kinetic energy is scalar, potential energy is scalar. Any kind of energy we introduce, it has to be scalar. Of course, in this case, potential energy can be positive or negative, but it is a number.
All right.
Good. Thank you.
All right, William. Thank you.
So now, okay, I want to introduce something called conservation of mechanical energy. And maybe I can introduce this and give like a break. So last week, if you remember, we actually introduced something called work energy principle. Maybe we should have called it work kinetic energy principle, but it was work energy principle. I remind you something like that. Net work done on an object was equal to change in kinetic energy. And now, okay, I generalize this. Okay, we need to incorporate potential energy. And now I think we already like convince ourselves that, you know, change in potential energy is equal to work done on the object. So I write it, maybe I write the result and let you stare at it. So okay, maybe delta U calculate. Let's say there's like a gravitation force. There is also like some external force. It is going to be minus 1 to 2 F dot dl, and this is equal to minus net external work done. Then from here, okay, we can combine these two things. I mean, I'm combining this line and this line. First, I use the information from last week, which was change in kinetic energy was net work. Now I use the information from this week. So, okay, I think it's a simple to combine these two things, right? It's like delta K plus delta U is equal to 0. So, which says total mechanical energy is conserved. Okay. So this is pretty convenient because if you calculate this whole thing for once, like say you calculate 1/2 mv squared, and you calculate the potential energy U. So this is constant. This is the constant, so you can use this constant to determine the motion at any other moment in time. So it is K1 plus U1 is always equal to K2 plus U2 at some other point in time. And here's the example. Here you are releasing the rock, and the total energy is only potential energy, and kinetic energy is 0. somewhere in the halfway, kinetic energy and potential energy like almost half by half, but their sum is still equal to this initial sum. And at the end, you don't have any potential energy, considering the reference point to be the ground, only kinetic energy, but this sum u plus k is still the same constant. Okay, let me read this question and give you a couple of minutes, and then I can attempt. A ball of mass m given, starting from s, falls a vertical distance h before striking a vertical coiled spring, which it compresses an amount y. Okay, here's the figure. Determine the spring stiffness constant of the spring. Assume the spring has negligible mass and ignore the air resistance. Measure all distances from the point where the ball first touches the uncompressed spring. Let's take y is equal to 0 at this point. So the ball starts here. And okay, the mass is given. And we are saying that it falls. And when it hits the spring, it starts compressing the spring. And when it reaches the maximum compression, it stops right here, right? Here you have only gravitational potential energy with respect to this reference point. Here you have only kinetic energy. And here you only have spring potential energy. And our task is to determine the spring stiffness constant K. What is it? All right, let me start. Okay, like I said, we take our reference point here. So let me write y is equal to y1. I have gravitational potential with respect to y is equal to 0. It's equal to mgh. Kinetic energy is 0. And we have a spring in this problem. Let me call it like potential energy of the spring is equal to 0. So at y is equal to, okay, y1 is equal to, okay, let me just write y is equal to h here. And now y is equal to 0. Gravitational potential is 0. Kinetic energy is 1/2 v squared. And u spring is equal to 0. From here, I can calculate 1/2 v squared should be equal to mgh. Cancel this and that. And v should be equal to root 2gh. Any questions, any objections? And finally, y is equal to something like minus y. Gravitation potential is minus mg. Y is below my reference point. Kinetic energy is 0. And u spring is equal to 1/2 my squared. Now I know 1/2 my squared minus mg y should be equal to mgh. Cancel m, cancel m, cancel m. And here, okay. This is like a quadratic equation, but I think y is given.
Hocam pardon.
Luckily,
Why you
yes.
say 1/2 multiply m? Isn't it k?
Oh, sorry. Yes. I think that's, I don't know what I was doing. Thank you. Yeah, that's wrong. Thank you. 6k, so there's no cancellation of m. I think I got into this cancellation too much. This is M, this is M. And we are trying to solve this problem for, like, M is given, H is given, of course G is given. We are trying to solve this for K. And I think I can solve this for K. So this is what? K is equal to mg h plus y divided by y squared, and there's an overall 2. Good. Any objections? Maybe I ask you to calculate this number and let me see what I found in my notes. Found something like, okay, 1,500, something like that, Newton per meter, right? And of course,
Yes.
yeah, I didn't do a good job with significant digits. Maybe I did. There's like 3, 3, and 3, and I had 3 digits. Okay, that's, I think, what it should be like. Good. Any questions? Okay, let's solve one more problem. So this is like a swinging pendulum, and a simple pendulum shown in figure consists of a small bob of mass m suspended by a massless cord of length L. The bob is released without a push at t is equal to 0, where the cord makes an angle theta is equal to theta naught to the vertical, this angle. A, describe the motion of the bob in terms of kinetic energy and potential energy, then determine the speed of the bob. B, as a function of position theta as it swings back and forth. And C, at the lowest point of the swing. And D, find the tension in the cord. F sub T, ignore friction and resistance. This is an example that this kinetic energy we introduced makes it really easy, right? So I describe the motion of the bob in terms of kinetic energy and potential energy. So this is easy. So here I have a potential energy and 0 kinetic energy, right? It's like completely stationary at this point, but the height, I take my reference point, this lowest point, y is equal to 0. It's completely potential energy. As it starts decreasing, some of this potential energy will convert to kinetic energy, and the speed will be non-zero. For example, when I reach to this point, the lowest point, I have 0 potential energy because I am in my like ground level, and I'll have the maximum kinetic energy. But the bob will not stop here; it will keep moving. There is no reason for it to stop because it has some energy, and as it rises, this kinetic energy will decrease, converting it back to potential energy. And when I reach here, I have complete potential energy and no kinetic energy. That's the description. Okay. And B, so determine the speed of the bob. B as a function of position theta as it swings back and forth. Okay, let's do that. Maybe I can take a general position like this here. And here, okay, initially, okay, this is B at y is equal to y naught. I have u g is equal to what? Mg y naught, but I think I can calculate it in terms of angle. If this angle is given here, this is L. I can project it to here. This is L cosine theta. And the difference here, L minus L cosine theta, is my net height. So let me write it in terms of this. This is going to be mg, okay, mgl 1 minus cosine theta naught. Now at this intermediate point here, I have some potential energy. Okay, let me write it Y as a general Y. Here, kinetic energy is 0. Now UG, we already calculate this, MGL 1 minus cosine theta. Now this theta is some other theta, which is not necessarily theta naught. And kinetic energy is going to be equal to 1/2 mv squared. If the energy is conserved, these two sums should be equal. Then 1/2 mv squared plus mgl 1 minus cosine theta should be equal to mgl 1 minus cosine theta naught. And what I have here is, okay, I take this guy to here, and maybe I can combine. This is mg L cosine theta minus cosine theta naught. And I think I can cancel m's. So this is gone. And this one is V2. And I'm going to take root. Something like that, if I didn't mess up. Check. Yes, good. C at the lowest point of the syringe, A, B, C, this is Y is equal to 0. V, okay, at the lowest point, okay, do that. So at the lowest point, theta is equal to 0, right? Maybe I can write this. Means theta is equal to 0. Then V is going to be equal to, and cosine 0 is 1, so V is going to be equal to 2 times G times L, 1 minus cosine theta naught. Good. And A, B, C, D, find the tension in the port, ignore the friction. Okay, I think, are we at the lowest point, or is it in general? I think I'm going to find the tension in the general point. I think, let's say it is in some location like here, and maybe I can write the free body diagram. So here is your mg, here is your tension, and the motion is at this moment, and at any moment, is perfect circular motion, always tangent to this circle. And we already have V, and find tension. Okay, T, I'm going to project this to here, minus mg cosine theta should be equal to what? Maybe I ask you. I calculated the tension here, T, and subtracted from that this component of the force, and what remains is total tangential force, total centripetal force. And the question is, what is this equal to? Total centripetal force in a circular motion. Anybody?
T minus mg cos theta. Theta.
Yes, I wrote this, and I need to write this is equal to something to solve it, right? And this is a perfect circular motion. And what do we know about circular motion?
Over L. We can find
Yes,
the.
yes.
We can
And we
find the
square-
period and pardon, omega from
Yes.
the high school.
I think somebody already called the answer. The
mv square
tangential acceleration.
is divided by L, isn't that?
Yes, mv squared over r. R in this case, which is L, right? So this is a perfect circular motion. Then, okay, this is the net force towards the central. This is the net centripetal force. And total centripetal force should be equal to v squared over r in circular motion. And this is more convenient because I know what v is. I can, okay, let me write this. This is m over L, and v squared is 2 times g times L, 1. Okay, it is not 1, it is general theta. This is cosine theta minus cosine theta naught. Cancel. Hopefully, can I cancel m's? No, I'm not going to cancel m's. We are trying to find tension. And tension is, okay, T is equal to, maybe I can cancel these L's. L and L. And T is equal to mg. I have cosine theta times 2. 1 more cosine theta is equal to 3 cosine theta. 3 cosine theta. And I have 2 times cosine theta naught. 2 cosine theta naught. And that's my answer, right? Hopefully I didn't mess up. Any objections? So you can see, like, I think this example is a good demonstration of this method, right? When you are using energy, things become really simple. Like even here too, right? You could, of course, solve this problem in terms of Newton's laws and forces and free body diagrams, but that would be like a torture. When you use like energy, it feels like a 2-line, 3-line calculation, and same in here, right? If you're careful, lay out all the energies, you have like a much simpler approach. Any questions? I think that's why most of you wanted to use energy last week. I was just trying to, demonstrate that we could actually solve it by using the forces, even though it was not as nice. But you were trying to like get back to like potential energy, and yeah, I think it's over here. Yeah. Any questions before I continue? So maybe I can introduce the most general form of this energy concept. And the most general form is, okay, change in total energy, change in total. And here, okay, this is equal to, of course, there's like kinetic energy, plus there is potential energy. And if I only have potential energy, of course, I only have conservative forces. But let me also put other like dissipative forces, or like friction, resistance, whatever. And the rule is this whole thing should be 0. Total change is always 0. Energy is conserved in nature. One of the most powerful laws of nature, right? For example, here, just to remind you, this is mechanical energy. And this part could be any kind of dissipative energy, like maybe I write it like non-conservative. It's probably better. Non-conservative. And inside this form, there could be like a dissipation, like friction. There could be chemical combustion, like if you are using your car, there's like a chemical energy, you burn it, and the fuel gives rise to like this heat energy, and you convert that heat energy to mechanical energy, move your car, right? Or it could be like a, I don't know, electrical or battery electrical energy, all these things. All the things that we don't consider, we can put it in these non-conservative forces from the mechanical point of view. And the rule is, okay, here, maybe I write this. Total energy is always, and this is always conserved. Any questions, any comments? And now let me incorporate these dissipative forces into like work done here. Let me just, we know now the total energy conservation. Let's also include the work done by the dissipative forces, right? For example, work by friction. Okay, let me call it W friction is equal to, and we know friction and the displacement will be always opposite, right? I will put minus sign and force friction dot dl, and this is in general something like minus constant times some delta L, total displacement. And now I can put this in with the all the work energy principle, right? Okay. W net now is going to be equal to W conservative plus W non-conservative. And here I have, I don't know, spring, gravity, like in the previous example, and here's friction. And we have, okay, what do we have? We should have total change in, total change in kinetic energy plus total change in potential energy should be equal to, of course, I'm using the same logic I used in the previous page. I use like work energy principle, change in kinetic energy, but I think it's easier to write the result and then justify it. So I'll write it like work done non-conservative. Okay, if you have friction, this is minus F friction times delta L. So what this says is your total change in mechanical energy is equal to the loss of energy. And here I actually brought the example from last week. Last week I was trying to solve this problem only using kinetic energy, and I was trying to tell you that there is no potential energy yet, but there's only kinetic energy and there's only forces. And at the time I was using like force on the block from the gravity, and I was using the work done on the block by the gravity, and some of you were pointing out though there's like potential energy. And here I bring it back. Actually, you could solve this same example, solve using energy. Maybe I can write kinetic plus potential energy. And compare last week. You can go to last week's lecture and see how we did it and do it with this week. Okay. So let me, Now I want to like generalize this gravitational potential, right? Initially, I was saying that gravitational potential is basically mgh, but this is not entirely true, right? This is only true if you are close to Earth surface. So in the general case, we have to think of this Newton's law of universal gravity, and we need to calculate the potential energy related to that. Right? Let's do that now. So force due to gravity, we know force due to gravity is G and M divided by R squared. So I can calculate the work done by gravity by this force. Let me call it work done by gravity on an object. And the definition is 1 to 2 Fg dot dl. And you can think of this picture. object goes from point 1 to point 2, and gravitational force always acts towards the Earth, and there is some displacement dl. Okay, these are vectors. And when you take the dot product, you are going to project this dl along this direction. So this dl is going to be dr, and there's like 1 over r squared here. So then if you write this, I have something like this. And of course, gravity is down here. Let me take that convention. This is minus g m m. So let me call this from r1 to r2, 1 over r squared dr. And when you take this integral, I have something like this: g m m 1 over r2 minus 1 over r1. And here, okay, here's your task. You need to show this is this agrees, maybe this agrees with mgh. Okay, and the way you show this is like as follows. You say r1 is equal to Earth radius, and r2 is equal to some Earth radius plus h, and h is much smaller than Earth radius. Okay, maybe I can take this in a bubble, not to confuse the other things we are doing. Finally, let me define, okay, this is work done on the object by the gravity. Now I want to define gravitational potential u. Okay, use gravitational potential, potential energy, exactly what we did. U of g is equal to minus the work done by gravity, and it is equal to g m m, okay, 1 over r1 minus 1 over r2. Good. And sometimes we say, okay, you can take the reference points. Take, for example, take your reference point r1 to go to infinity. So what is your energy to bring an object from infinity to a position r2, right? You can take r1 to infinity in this equation, and what you'll find is okay, so take r1 goes to infinity, then gravitation of r is going to be equal to minus g m m over r. So this is energy to bring a mass m from infinity to a point r. Then you always need to have this reference point here, right? We are taking our energy to be 0 at infinity. Good. And this is the definition of gravitational potential. So this is gravitational potential energy. Of course, this is defined, like I said, up to a constant. Good. Any questions? Any objections? And if you plot this function, it is something like that. It is always negative. And as you go to infinity, it goes to 0 because 1 over r. And as you go to r is equal to 0, if you go to Earth's core, for example, it diverges with 1 over r. I took R2, yes, you can take one or the other. I took are, I said, so this is the work done starting from 1 to 2, right? You bring a particle from 1 to 2, and I think I bring a particle from 1 to 2, and that's how I defined it. Good. So here, actually, there is something interesting I want to define. Okay, maybe I want to define something called escape velocity. Now I want to calculate the total energy at any given point. Let me calculate it at some point. 1/2 mv1 squared minus g m divided by r1 squared. Assuming there is no other force, and we should have this is equal to 1/2 mv2 squared minus g m over r2. Now I send one of these R1 or R2 to infinity. Let's say this goes to infinity, and let's assume that V2 is equal to 0 at infinity. So I say that, okay, let my mass go to infinity with 0 velocity, like 0, and R2 goes to infinity. And this condition defines escape velocity. Let me call it like escape is defined by the solution of this 1/2 mv squared minus g m over. And you start from Earth's surface. If you like, I can call it like R naught is equal to 0. And if you solve this equation, the escape is something like that. You cancel m's. 2 g m over R naught, something like that. And here you have all the masses. You have you have the Newton's constant, you have the mass of Earth, and you have the radius of Earth. If you put these numbers, you found something like 10 to the 4 meter per second. So I think 1.1 both times 10 to 4 meter per second. And this is like a huge number. And of course, if you didn't have the atmosphere, you could, and if you could throw something with this speed, it would just go to infinity. But because there is an atmosphere, if you throw something with this speed, it's going to burn in a matter of minutes, because this is a gigantic velocity. That's why meteorites, when they dive in, they burn because of the atmosphere. Okay, so this terminal velocity is interesting, but in practice, it's useless. That's why rockets use constant, they have completely different approach. NASA is not sending the rockets with the speed from Earth. They slowly go and they minimize their friction because they don't want to burn their space shuttles. I think I want to quickly introduce one more concept.
I didn't understand why we subtract the energy, why we energy minus force, why we did do this.
So,
I don't understand.
Which line you are talking about? This line?
Can I annotate this line again?
Yes. So I said so I defined gravitational energy as the minus the work done by gravity on the object, like we did all along. And I said, what is the work done to go from point 1 to point 2?
Evet, anladım. I understand. Thanks.
Yeah. So it is a little bit confusing, but I think if you remind yourself, okay, what is the work I should do on an object to bring it from infinity to this point? Also, what is the work done on the object by the gravity. These are two different things, right?
Yes, right.
But like I
I
said, yeah, like I said, I think this is a little bit more like definition, but yeah.
I just see the R sub 1 like R sub 1 square. I thought it is a force. Now I see. Okay, it's energy.
There's no square. Yes.
Yes.
Yeah, there's no square. If you have 1 over R square, it is force. If you have 1 over R, it is the energy.
Yes.
Good. Thank you.
Thanks.
Any other questions? Any other concerns? We struggle with Earth's force, right? Yes. So maybe I can quickly introduce one more concept and finish it here. I want to introduce something called power. And the power is, okay, here's the definition. Work done per unit time. So of course, how much work you do is important, but how much you do in a given time is also important. And we quantify this with the definition of power. And to do this, okay, we have to do what we did all along. We need to first count because unit time is division by time. So when we divide with time, we first introduce average power. And we show it with P, and this is the average total work done divided by time. And then we also introduce the units. Work unit is joules, and time unit is seconds. Joules per second is called sometimes watt. And I think in the old days, they used to also call it like horse power, right? Something like HP, I think they use the lowercase, something called HP. I think nobody uses that as much anymore. Maybe in car industry, they use a little bit. And this conversion is actually calculated by, I think, Watt himself. And 1 horsepower is about 746 watt. And Watt actually calculated this by using his forces. For some reason, I think that's why it's still called horsepower. It's completely arbitrary, but it is what it is. So once we have the average power, we can calculate the power or instantaneous power as we did all the time. Like maybe I'll call instantaneous power is P without any bar, and it is going to be equal to, as you know, dV dt. Okay. So okay, now here's the perspective. When you do work, you transfer energy, right? For example, when you push something, you do work, and that work is transferred to the object as a kinetic energy. And the total energy transfer is, or like energy transfer per unit time is power, right? P is equal to E dt. Now I want to calculate that. Power is equal to E work dt, and it's equal to D dt. Let me put what work is. Work is, okay, I can actually put it in the integral form, but let's write it F dot L. And if you assume F is constant, you can put the L. Okay, let's assume F is constant. This is going to be F dl dt, but dl dt is velocity, so it's going to be force at velocity, right? And that's your power. And here, like if you are doing with an engine efficiency, so it is defined by, I think, is there like a symbol for efficiency? It should be some Greek letter, but I think for this course they are using E is equal to power out. How much power can you get out of a machine given the power in? And typically this is much less than 1. For example, for state-of-the-art cars, like most modern cars, they have like an efficiency around, I think, 15%. And this is a lot of wasted energy, right?
Yes. By the way, hocam, the letter of the efficiency is eta.
Eta, yeah, okay.
Yes.
Maybe I can, something like that. For some reason, this book uses E, but that's fine. I think in the future, I think you guys are going to use it a lot because this will be important for you, but you know, you can maybe be in line with this Giancotti notation for the moment. Okay, any questions? Hopefully you guys can find ways to make this better in your future careers. Okay, let me finish one more thing. And so this is about the potential energy. I said potential energy is actually like a different way of looking at problems. And in some cases, potential energy is more fundamental than force. So given the potential energy, you can calculate the force. And the idea is you can actually do more than that. Given the potential energy, you can describe the entire motion. Suppose I give you a potential energy curve like this, something like that. And I ask what happens, right? And you should immediately ask, what is my total energy? Because potential energy is a landscape. And in that landscape, you can have different energies. And okay, if my energy is somewhere over here, for example, E naught, I can highlight this, E naught, my motion is going to be frozen here because I cannot go anywhere, right? So if my total energy is here, I need some energy to go up the hill, but I don't have it. So here is E naught is going to be stationary. And if you are given to have energy like here, E1, you start here, and since you have energy, you can start rolling down, and you can convert this potential energy to kinetic energy as you go down here. For example, here you converted entire kinetic energy to entire potential energy to kinetic energy, and you keep moving, and you go up here by converting that kinetic energy back to potential energy, and you go back and forth, back and forth. E2 is a little bit more interesting. So if your energy is given to be on this level, you have two possibilities, right? You can do this back and forth either here and here. So now it is like an initial condition dependent. So if you are given to be here initially, you are going to be oscillating here forever, and you are not going to see this other minimum. Or if you are given to be here, you are going to oscillate here back and forth without seeing anything here. And finally, if your total energy is here, you're going to roll down, go up the hill, roll down, go up the hill again, and go to infinity. Basically, the entire motion can be described in terms of potential energy landscape. Okay, maybe I can write given total E motion can be fully specified in terms of potential energy. I think that's all I wanted to say. If you want to leave, you can leave. I'll see you guys tomorrow. If you have questions, I'll hang out for a couple of more minutes.